Okay, welcome back, students. Let's continue on with section 9.2. Okay, 9.2 is on vector formulation. Okay, definition. The vector space VNI is the set of all column n vectors or n vector functions defined on an interval I. Okay, next definition. Okay, let x1, x2, ... to xn be vectors in VNI then the Wronskian of these vectors denoted by W of x1, x2, xn of t is defined by Wronskian of x1, x2, ... xn of t is equal to the determinant of x1, x2, xn of t. Determinant of this guy. Okay, theorem. Let x1, x2, ... to xn be vectors in VNI if the Wronskian of x1, x2, ... xn of t naught is non-zero at some point t naught in I, then the n column vectors x1, x2, xn k are linearly independent. On I. Okay, number one. Show that x1 equal to e to the t 2e to the t, and x2 equals 3 sine t and cosine t are linearly independent on the interval negative infinity to infinity. So let's look at the Wronskian of this. The Wronskian of x1, x2 is equal to the determinant of e to the t, 2e to the t, 3 sine t, cosine t. Okay. So the Wronskian is not determined here. It's a different definition of what the Wronskian is. We have Wronskian 1 and Wronskian 2. So this is Wronskian 2, where it doesn't have to do with the derivatives of the functions. Okay, this has to do with the elements of the n column vectors. Okay, but if we do that, if we find the determinant of that, that's why we defined it different above. We find the determinant of this, this becomes e to the t cosine t minus 2e to the t sine t. I'm sorry, that's 6, my bad. 6e to the t sine t. Okay. So we just need to find some value where this thing is not equal to 0. Okay, so let's let t naught be equal to, say, 0. Then w of x1, x2 at t naught is equal to e to the 0 cosine 0, oops, minus 6e to the 0 sine 0. Okay, and that's going to equal 1, which is not equal to 0. Okay, thus, since there exists a t to the 0, in this case, 0. Okay, and it didn't have to be 0. We could have chosen something else that makes it non-zero as well. Okay, we just chose 0 to make the computation easy. Okay, in this case, 0, such that the Wronskian is not equal to 0, then the column vectors x1, x2 are linearly independent on negative infinity to infinity. Right? Okay, let's do another example. Number 2. Okay, show that x1 equaling e to the t 2e to the t, and x2 equaling 4e to the t 8e to the t. Oh, these should be 2 t's, I'm sorry. This is e to the 2t, and this is 8e to the 2t. Okay, show that these guys are linearly dependent on negative infinity to infinity. Okay. Well, let's look at the Wronskian of this. The Wronskian of x1, x2, okay, is going to be equal to the determinant of e to the t, 2e to the 2t, 4e to the t, and 8e to the 2t. This is going to be equal to e to the t times 8e to the 2t minus 2e to the 2t times 4e to the t. So this is equal to 8e to the 3t minus 8e to the 3t, which is 0 for all t. Okay, so there is no t value that will get these to be non-zero. They're always 0. Therefore, thus, the system okay, is linearly dependent on negative infinity to infinity. Okay, we can also see that 4 times x1 is equal to x2 by inspection. And thus they're, x2 is just a multiple of x1. Okay, so this kind of, checks that, yeah, we set it up so that they would be linearly dependent, just to show that the Wronskian does work to prove that to be true. Okay, let's look at a final definition here. Okay, a system of linear differential equations written in the vector form x prime of t is equal to a of t times x of t plus b of t is called a vector differential equation. Okay, where x prime of t is equal to x1 prime of t, x2 prime of t, all the way to xn prime of t. Okay, a of t is equal to, okay, a11 of t, a12 of t, dot, 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 to a1n of t. And then this goes A21 of t, A22 of t to A2n of t. This goes all the way down to AN1 of t. And this is AN2 of t. And dot, 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 until we get to ANN of t. Okay, so it's a square matrix. Okay. And then B of t is equal to things that don't involve x1s or x2s. It's just B1 of t, B2 of t, all the way to Bn of t. Okay, and x1, or just x of t, I should say. Okay, x of t is just equal to the results that I would want, which is x1 of t, x2 of t, and xn of t. Okay. Okay, where x prime of t, x prime of t, b of t, and x of t are all column n vectors. Well, vector functions, sorry, not vector, vector functions. And A of t is a square n by n matrix. Okay. Okay, that's section 9.2, which basically sets us up for section 9.3 with all these definitions and the Wronskian. Okay. Okay, I'll see you in the next section.